So for this problem, let's take our system to be the two masses in the teeter-totter. So we're given in the problem that the system is at equilibrium. Now, in order for the system to be at equilibrium, the teeter-totter must be balanced, which means that the fulcrum is located right beneath the center mass of the system. So let's first calculate the position of the center of mass with respect to the left end of the teeter-totter. So we know that the fulcrum is located at a distance x from the left end of the teeter-totter. So the center of mass is located at x. And that is equal to, well, the m1 term is cancelled out since it remains at the origin. So we have that x is equal to m2 times L, which is its distance from the left end of the teeter-totter, divided by the total mass of the system, which is m1 plus m2. Now we can solve for m2. So moving the denominator to the left-hand side, we get that m1 times x plus m2 times x is equal to m2 times L. And now, grouping up the m2 terms and factoring out the m2, we get m2 times L minus x is equal to m1 times x, which means that m2 is equal to m1 times x all over L minus x. So that's our final answer for part A. Now for part B of the problem, we have to show that for small tipping angles, delta theta, the sum of the gravitational potential energies of mass 1 and mass 2 do not change, which would mean that the total energy of the system remains constant. Now, the change in the sum of the gravitational potential energies of the masses is given by m1 times g times delta y1 plus m2 times g times delta y2. Now, for a small tipping angle delta theta, mass 1 will move down a certain distance, while mass 2 will go up a certain distance. Let's call that delta y1 and delta y2. So delta y1, the change in the vertical position of mass 1, is given by negative x delta theta, small angles delta theta, and delta y2 is given by L minus x times delta theta. Now if we plug that in for delta u, we get that delta u is equal to m1 times g times negative x delta theta plus m2 times g times L minus x delta theta. Now we can plug in our value for m2 from part A, which would give us negative m1 gx delta theta plus m1 times x over L minus x times L minus x delta theta. So the L minus x cancels out, so we get that that is equal to negative m1 gx delta theta plus m1 x, sorry, we left over g here, g delta theta. As you see, these two cancel out, so that is just equal to 0. So we've shown that delta u is equal to 0, which means that the change in the total potential energy or total gravitational potential energy of the two masses is 0. Therefore, the energy of the system must remain constant.